Welcome students. Today we are going to start chapter number 2 of class 12th physics. Chapter is electrostatic potential and capacitance. So we should start from the first topic of second chapter, electrostatic potential energy. Consider an electric field due to a charge capital Q. Capital Q is a charge, positive charge, which is kept at the origin. Let us assume the capital Q charge is at origin, and due to the electric field of this capital Q charge, okay, there will be uh, an electric field in the surrounding of this capital Q charge. And let us consider one test charge, small q. It is also a positive charge, and let us try to move this small q test charge from point R to point P. In this situation, there will be two forces acting on this test charge. First force is due to electric field of this capital Q charge. We know that whenever there are charges of same polarity, they will try to repel each other. They will repel each other. So this capital Q charge will exert a force on small q charge, which will be repulsive force. And since we want this charge to move towards capital Q from point R to point P, so we have to apply some external force. And that external force should be just enough to cancel this repulsive force due to electric field of charge capital Q. Once the two forces, first force is electric force due to electric field of charge capital Q, we can say it is electrostatic force. This is external force. So there will be two forces acting on this small test charge, which is near to this capital Q charge. There will be a repulsive force due to electric field of capital Q charge, and there will be an external force. There will be an external force on this charge, applied by us, so that this charge can move from point R to point P. This external force should be just enough to cancel the electric force or electrostatic force due to charge capital Q. Once the two forces get cancelled out, this small test charge will move slowly with constant speed from point R to point P. Now if you want to calculate the work done in moving test charge from point R to point P, then that work done will be negative of the work done by the force which is due to electric field of positive charge. Because we know when the charge will move from R to P, the displacement of the charge will be in opposite direction to the electrostatic force. So we can say the work done by the external force in moving charge from R to P will be equal to negative of the work done by the electrostatic force due to charge capital Q. The work done by external force in moving charge from point R to point P will be stored in this charge in the form of electrostatic potential energy. So we will now try to write the equation for the work done in moving this charge from point R to point P. This is the work done in moving the unit test charge, okay, in moving this charge from point R to point P. So we can calculate the work done using integration, and we will integrate the force and the displacement. This will be equal to negative of work done by the electrostatic force which is due to capital charge Q. Because we know that this capital charge Q will be having an electric field, and this small q will experience an electrostatic force which is equal to QE. So this electrostatic force, okay, this will try to repel this small q. So work done can be written in terms of external force, and it will be equal and opposite to the work done due to electrostatic force. At every point in the electric field of this capital Q charge, any particle of charge small q will possess some electrostatic potential energy, and the work done will increase that potential energy. So when we do some work on this test charge, and if the work is increased, work can be increased by moving it further closer to this capital Q. So if you keep on moving it towards capital Q, you are actually increasing the work done. And as you increase the work done, the potential energy increases. The potential energy, electrostatic potential energy of this charge small q will also increase. Now we will see how to derive the formula for electrostatic potential energy. See, the increase in this potential energy moving from point R to point P is actually the difference of electrostatic potential energy between these 2 points. जितना भी आपका पोटेंशियल एनर्जी है, जो आप पोटेंशियल एनर्जी इस स्मॉल टेस्ट चार्ज को दे रहे हो इन द फॉर्म ऑफ वर्क डन, दैट increase in work done, that increase in work done will actually equal to potential energy difference between these two points. And when I say potential energy, तो जब भी potential energy हम यहां बोलेंगे तो it means it is electrostatic potential energy, because this small test charge is placed under the influence of electric field of capital Q charge. So I can write the expression for potential energy difference. So this potential energy difference between these 2 points will actually equal to work done in moving this charge, test charge, from point R to point P. Now, to define potential energy at one single point, we will assume that this charge is moved from infinity to point P. It is easier to, to assume that potential energy is zero at infinity, because as this charge small q comes closer to capital Q, potential energy increases. Potential energy of this test charge goes on increasing. So we can assume that at infinity, the potential energy of this small q is zero. Let us consider that capital R, this point capital R, is at infinity. So I can write and R is infinity. And at infinity, the electrostatic potential energy is considered zero. So we can define the electrostatic potential energy at point P, at any point P. Electrostatic potential energy at any point P is actually the work done in moving a test charge from infinity to that point P. Now we will see what is electrostatic potential. If we divide the work done in moving test charge from infinity to point P by a unit positive charge, or you can say unit test charge, then it becomes the characteristics of the electric field, and it gives us idea of the electrostatic potential. Now let's see the potential due to a point charge. Students, look at this diagram. In this diagram, there is a charge capital Q which is fixed and it is at the origin, and this is the point P where we want to calculate the potential due to this charge capital Q. This is small r and this is the unit vector pointing towards this point P. Now, how to find out the potential at this point P? From the definition, we know that the potential at any given point is actually is the work done in moving a unit positive charge from infinity to the point. If we want potential at this point, we have to find the work done in moving a test charge from infinity to this point P. To get the work done, to find the work done, we will take one intermediate point P dash, and firstly we will try to find the work done in moving test charge from P dash to point P. We want a small work done in moving a small distance P dash to P. In moving test charge very small distance delta R dash, the work done will be very small delta W. This work done will be equal to force multiplied by the displacement. Now the force, suppose this positive charge is at point P dash, the force will be in this direction and this force will be electrostatic force, because this capital Q charge will exert electrostatic force on this small q charge. So I will write here this electrostatic force. We know the formula of electrostatic force. When at the time when small q is at P dash, the distance between small q and capital Q would be R dash. So I am writing R dash square. So this is the, as per Coulomb's law, this will be the force when Q is at P dash. Now we want to move this small q. How much distance? Delta R dash. So I will write multiplied by delta R dash. Still, it is not correct. Why? Because the force is in opposite direction of displacement. Force is in this direction and the charge is moving in this direction. The displacement is towards capital Q and the force is towards small q. So we have to put a negative sign as well. Now how to find the total work done? Total work done means work done in moving this small charge, test charge, from infinity to point P. Infinity to point P. Start. Assume that small q is a unity test charge. So small q is 1 coulomb charge. So delta W will be equal to minus q upon 4 pi epsilon naught R dash square. Small q we will put as 1. So substitute 1 for small q, you will get this expression. By integrating this equation, we can get the total work done. Left side will become W and you integrate this. The lower limit will be infinity because we are bringing the charge from infinity to point P. Inside the bracket q upon 4 pi epsilon naught R dash square dr dash. So you integrate this thing, q is constant, 4 pi epsilon naught is constant. Now 1 upon r dash square integration is minus 1 upon r dash. Minus minus will get cancelled. And the limits are infinity to p. So when you will put the limits, lower limit and higher limit, then you will get W is equal to Q upon 4 pi epsilon naught R, because 1 upon infinity is 0. This work done is basically the potential at point P. So students, this is the voltage, or you can say potential at point P, which is equal to Q upon 4 pi epsilon naught R. So we can say that the potential at any given point P depends upon the magnitude of the charge and the distance of the point P from the charge. Thank you so much. Thanks for watching, and for more such videos, subscribe to our channel.